Starting now. Okay, so here we are. So on the old suspension bridge thing is we have two unknowns. So we've got a mass of a gray thing that's uniformly distributing the mass. Well, I don't know if that's actually, I don't know if it's uniformly distributed, but I do know the center of mass is right there. And I know this is 0.6 kilograms there. And if I click on my ruler, it'll tell me exactly where those things are. Okay. And so while I'm here, I'm going to actually write down exactly where they are because those are going to help me solve for what the tension is here and what the tension is over there. Okay. So I need to know exactly the location of all those things because here's why, guys. I don't know. I have two unknowns. But if I use rotational equilibrium, I can get it down to one unknown. I'll show you why in a second. But before I do that, let me write down exactly the positions going on here. And I'm checking out a chat. Well, my chats, I can't see my chats behind here, guys. I'll have to look at that later. So on my ruler, this is in centimeters. My center mass of my gray thing is at not quite 54 because it goes by twosies. It's 53.5, I think. Okay, so I'm going to write down, so I don't forget this, that, oh, there's my chat. It popped up all of a sudden. Is one student view slightly different? It is, because the student view one doesn't, I can't click on my forces and it doesn't tell me what the forces are. Other than that, it's the same. Okay, all righty. So now let me get rid of, move that chat over there. And let me start drawing again. So my center of mass is at 53.5, I think. That's the center of mass of my stick right there. I'm writing it down because I'm going to scribble a bunch and I might not be able to see it. And then my mass here is hanging at 82.5 maybe. Okay, I'm going to need that in a minute. So 82.5, not quite 83. It's 82.5 centimeters. Okay. So here's how I'm going to get rid of one of my unknowns. I'm going to use rotational equilibrium. I'm going to put my fulcrum at one of two places. I'm going to put it at the red spot, or I'm going to put the green. I'm going to choose red at the 0. So the reason I'm going to put my fulcrum here, I can put it wherever I want to, guys. It's my problem. But if I put the fulcrum here, that means that adds 0 torque. So there's a force there, but the lever arm is 0. There's 0 radius distance there. There's no torque, but there is there. Now I only have one unknown. And I have got my distances written down where the weight of the gray thing acts and where the mass of the blue thing acts. So now I'm going to hide my ruler. I've got those distances. So to set up my problem, all I have to do is set up my torque problem. So now I have a tension pulling upwards, and that's going to be a counterclockwise torque. So, but that's my unknown tension or my unknown force. Oops, here's one thing I forgot to do, guys. One thing I forgot to do is write down where that thing is. This is at 106, 107.5, maybe 107.5. Okay, hiding my ruler. So right now that is from the fulcrum at 107.5 centimeters. So for my counterclockwise torque, I have a force, unknown force, acting at a distance of 107.5 centimeters. Okay? Now that's the only thing I have twisting opposite of a clock. The only thing. Everything else acts clockwise. The weight of this bar right here acts right there. That goes clockwise. The weight of this blue thing acting right here, that goes clockwise. That's going to be on my other side. But this is in kilograms, so I have to change that to a force because I actually have to solve for the tension in force units, not kilograms. Okay, let me do my bar first. So I have 1.7 kilograms, so I have to change that to force. So 1.7 kilograms times 9.81. I want to be as spot on as I can be. And then times my distance from my fulcrum, which is 53.5. Now you might say, hey, Mr. Olson, that's not in meters. Yep, you're right. Everything is going to be in centimeters. They're going to cancel out. It's not a big deal. Okay, so what I didn't leave a lot of room for is for now this torque that's going to go clockwise. I'm going to try my other side over here. It'll still fit on the screen. So over here, I've got a 0.6 kilograms, and that's 0.6 kilograms times 9.81 times its lever distance, which is from the fulcrum, 82.5, what I'd used with my ruler a moment ago. So that is 82.5 centimeters. These are the two added together torques that are clockwise that are equal to my lone counterclockwise torque. I'm going to solve for that force right now. Okay, so solving for that force right now, I've got a 0.6 times 9.81 times my 82.5 centimeters plus 1.7 times 9.81 times 53.5 equals, so that's my total torque in centimeter newtons, 1377.78. Now I'm going to divide it by my distance over here. So dividing it by my, I can't remember if I hit the divided by sign yet. Okay, divided by, I did not, 107.5. Boom. That means my force on that green side right over there is 12.8. I'm going to go one more sig fig, 12.82 newtons. Okay, so that's on the right side over there. Okay, got it. 12.82. And you might say, hey, Mr. Olson, my homework says I have to do both. How do I do the other one? Well, guys, you got a couple things you could do. One is you could move your fulcrum to this side and repeat everything you just did and solve for the other side. But that would be the sucker's way to do this. The faster way is to use equilibrium, not rotational equilibrium, but equilibrium, the sum of all forces. Because here's what I have. 0.6 kilograms, guys. 0.6 kilograms times 9.81 is a weight of 5.89 newtons. 5.89 newtons. The weight of the gray thing, 1.7, whoops, I missed the button. I'm trying to look at the clock. 1.7 times 9.81 equals 16.68 newtons. So I add this weight plus this weight. The total weight of everything, guys, added together downward. So if this is a free body diagram, the total weight of everything downward is 22.57 newtons downward. It's in equilibrium, guys, meaning the total force upward has to be 22.57 newtons upward. 12.82 of that is on the right side. So if it's 22.57 upward, 12.82 is on the right side. All I do is subtract that 12.82 from that side. And that means what I have left over on this side is 9.75 newtons. And boom, that's the tension there. That's the tension on that side. And if I wanted to check, it's a pretty easy thing to do. All I do is click on this one since I'm in the actual, what do you call this? The lab side, and that's going to say 9.7-ish. Click on that. And on this side, it's going to be the 12.8-ish. And that's going to be good enough. On yours that you're doing for Student View, there's nothing to click on. It'll tell you if you nailed it or not. Okay? So I'll put a due date on this. I know it says today. You got other things that might be due tomorrow. I'm going to move the date till tomorrow. So by midnight tomorrow, have this 2-point exercise in student view completed and turned in, if you would. Okay. Questions, anybody? Questions at all? Anything I can answer for you? Because you have a whole 23 seconds left. There's a lot going on in there. So the key is to wrap it up. It doesn't look like a teeter-totter, but you can turn it into one by putting your fulcrum wherever you want to. But since I had two unknowns, I put the fulcrum under one of the unknowns. Now I don't have to worry about it. You solve for one, then you solve for the other one after you solve for that one. Have a wonderful day, guys. If you still have questions, hang around. I'll try to answer those for you. All righty.